Hello guys, and welcome to another calculus video. Today we're going to be checking out this differential equation right here. As you can see, this is the initial condition right here, and the final question that we're trying to answer is the limit as x goes to 1 minus of our function y of x. So without any further ado, let's go ahead and jump into this very golden differential equation. So this is a non-homogeneous differential equation because we have this section with the y's is actually being set equal to a function of x, not just equal to 0. So generally, the first step that you want to take to solve a non-homogeneous differential equation is to solve, or I guess you could call it a heterogeneous differential equation, is to solve the homogeneous version. So that would be x squared y double prime minus y equals 0. Now this is what's known as a Cauchy-Euler differential equation, and that's in general a differential equation of the form x to the n, y to the n, plus a x to the n minus 1, y to the n minus 1, plus b, and so on and so forth, equals 0. And so basically in this case, since it's just powers of x multiplied by the derivatives of y, such that the number of times y is differentiated is the same as the power of x. And these are pretty easy to solve because the type of solution is already known. So to solve this kind of differential equation, we just assume that y equals x to the m, where m is some number. So if we go ahead and substitute that into the equation, we will get that x squared x to the m minus 2 times m minus 1 minus x to the m equals 0. And as you can see, this and this are both just x to the m, and since x to the m can't be 0 across all domains, we can just go ahead and cancel that, and this just becomes a simple quadratic equation. And the solutions to this equation are very well known. You can use the quadratic formula, or notice that this actually denotes the relation m squared equals m plus 1, meaning that the solutions to this equation are actually the golden ratio. So that's phi. Sorry, that doesn't look too good. It's phi. And the other solution is called phi bar. It's instead of 1 plus square root 5 over 2, that's phi. There's also 1 minus square root 5 over 2, and those are our two solutions. So if we take our original differential equation here, once we solve it once, our total solution y is going to equal yc plus yp. And basically yc is the general solution, which would be c1 x to the phi plus c2 x to the phi bar, right? And the reason we have to include this yc is because once we find a yp, which is a particular solution to this differential equation, if we take that original solution and add these solutions in any form, if we look at the left side of the equation, adding these won't actually affect the value of x squared y double prime minus y, because they cause that to be equal to 0. So once we find any one solution to the original differential equation, we also have to add back in these other constants. So that's why we need initial conditions. So the only initial condition we're given is that y double prime of 0 is equal to 2. And so what I'm going to do is I'm going to show that both c1 and c2 have to be equal to 0. So actually, since we know that y double prime is equal to 0, or y double prime of 0 is equal to 0, we can go ahead and find y double prime of c, since y double prime is really y double prime of p plus y double prime c, right? So y double prime c is pretty easy to calculate. It's just c1 times phi minus 1 of x to the phi minus 2 plus c2 times phi bar minus 1 x to the phi bar minus 2. Now the interesting part is phi is actually approximately equal to 1.618, and phi bar, I don't know what it's equal to, but it's less, it's actually less than 0, I believe, right? It's a negative number. Yes, it's a negative number. So if we were to plug in y double prime of 0, assuming C1 and C2 aren't 0, we would actually get an infinite quantity. And so that actually does not work, because that would just, or I guess it wouldn't be infinite, it would technically be just undefined, right? Because we would be raising 0 to a negative power, and that just doesn't work. So that actually means that our C1 and C2 are going to be equal to 0. So that allows us to solve the differential equation much more easily. So now let's take a look at this differential equation once again. And generally, the way we would go about solving this differential equation is we would use variation of parameters, because we already solved the homogeneous form. Now we would solve the non-homogeneous form. The trouble with this is that this is quite a nasty function. So when we end up solving for this variation of parameters, it might work out for us, but it would generally be a lot of work. And that's made even worse by the fact that our general solutions to the differential equation, or to the homogeneous equation, are x to irrational numbers. You know, if it's rational numbers or natural numbers, those powers of x are relatively easy to deal with, but once we deal with irrational numbers, it becomes very hard to reconcile them with whole number powers. So instead, we want to search for another way to solve this differential equation. And that's where the masterstroke for this equation sets in. Now, a cool trick that actually works for quite a few different Cauchy-Euler differential equations is substituting in a power series. And that's actually perfect for this type of differential equation, because if you look on the right side, 1 over 1 minus x is famously equal to the sum of x to the n, right? Sum from n equals 0 to infinity of x to the n. And so, what we're going to do is a common trick which is used in differential equations, which is setting y equal to a power series. So let's say y equals the sum from n equals 0 to infinity of yn x to the n. This is just something we're assuming. And we can go ahead and simplify this side real quick. This is going to become x to the n plus 2. And if we go ahead and substitute on this side, we're going to get x squared times the sum from n equals 0 to infinity of the second derivative of x to the n, which is going to be n times n minus 1 times x to the n minus 2. However, since we differentiated twice, the first term is going to disappear, because before we did that, the first term is going to disappear because it was a constant, and the second time is going to disappear because it was x to the first power, so the second derivative of that is 0. So we need to shift the index over to 2, as so, right there. And then for this other sum, it's just going to be the sum from n equals 0 to infinity of yn x to the n. And we're going to set this equal to n equals 0 to infinity of x to the n plus 2. So first off, we want to combine these powers of x. So this just becomes x to the n. And if you notice right here, since this is x to the n plus 2, we want to sort of shift the index of this sum so that it matches up with these two sums. And then, instead of equating the sums equal to each other, since we have the coefficients of every power of x, we can just equate those coefficients, and once we solve for those coefficients, it should be relatively easy to solve for the original function, just using Taylor's series, right? So first thing we're going to do is we're going to combine these two sums, since their indexes now match up. Actually, wait, we can't do that yet. Sorry, 1 second. 0 to infinity. So we're going to shift over this right here. We're just going to have n, and we're going to have n starting at 2. So notice on the right side, our first term is the x squared term. We have no constant term, and we have no linear term right on this side. However, on the left side, this sum also has no linear term, or no constant term. However, this sum does include a linear term and a constant term. So we can assume that those linear terms and constant terms are both 0 because we're assuming that both sides of the equation are equal, because that's what the equal sign means. So that tells us that y0 equals 0 and y1 equals 0, right? And so we can just shift this index over to 2 because those first two terms are equal. Now, since our indexes match up everywhere and our powers match up everywhere right here, we can simply equate the coefficients on both sides. So the coefficient of x to the n on the left side is n squared minus n minus yn, and this is equal to 1 on this side. If we go ahead and factor out yn here, we're just going to end up with n squared minus n minus 1. And this tells us that yn is equal to 1 over n squared minus n minus 1. So overall, this tells us that our original function, y of x, is equal to the sum from n equals 2 to infinity. Because as you can see, we already stated that y0 and y1 are equal to 0, but this yn does not match up with this. So we just need to set those equal to 0 and exclude them from the sum of the sum x to the n squared minus n minus 1. And this is our function y of x. Again, we do need to say that y of x equals yc plus yp. And our yp is actually this function y of x. But as we said before, yc has to be 0 because otherwise y can't exist around 0. So the next step in solving this is our original question. So first off, one thing I want to state is that it's relatively easy to show that the radius of convergence of this series, r, is equal to 1, and that the interval is just going to be -1 to 1. So that means that this function is only defined between -1 and 1. Of course, our original function was defined in more places, so that original function would really be the analytic continuation of this function that we just derived. So really, we can say it's really the analytic continuation of this function right here. However, the question that we were originally asked was limit as x goes to 1 minus of y of x. So we can use this definition since we are staying completely within this interval. So in this situation, clearly this series will diverge for x is greater than 1, and the series will converge at x equals 1 and x is less than 1. So this limit as x goes to 1 minus is the same really as setting x equal to 1, since overall we're going to have the same result. The only reason we couldn't do a normal limit is because the limit doesn't exist from the right side, and also we can't define x equal to 1 in the original question because that would cause some problems because we had that x squared over 1 minus x, which would have been undefined. So we can just say that this is equal to the sum from n equals 2 to infinity of 1 over n squared minus n minus 1. And we're just going to use our normal methods to solve this. So the first thing we're going to want to do is use partial fractions to solve this. Now luckily we already know the expansion here. Since we already solved that quadratic equation earlier, this is just going to be 1 over n minus phi times n minus phi bar. Now one thing I want to do is I actually want to solve for phi bar right here. We know that when we expand this, we're going to get n squared minus n minus 1. This is equal to n minus phi times n minus phi bar. And if we go ahead and isolate the -1 term, you can actually see that phi times phi bar is equal to -1, because that's the only term that doesn't include any n. And so this means that phi bar is actually just equal to -1 over phi. I'm sorry, I keep saying phi. I know the correct pronunciation is phi. I've just always called it phi my whole life for some reason. I'm very sorry about the pronunciation. So this is actually the sum from n equals 2 to infinity of 1 over n minus phi times n plus 1 over phi. And we're just going to go ahead and use the cover-up method. So this is going to end up being the sum from n equals 2 to infinity. When we go ahead and plug in phi right here, we're going to get 1 over phi plus 1 over phi, which, using the properties of phi, 1 over phi is actually equal to phi minus 1, and phi squared is equal to phi plus 1. So we can just go ahead and say this is going to be 1 over 2 phi minus 1, n minus phi. And if we go ahead and plug negative 1 over phi right here, and then simplify, we just find it's negative the other thing. So it's going to be negative 1 over 2 phi minus 1 over n plus 1 over phi. All right. So we can go ahead and just factor that out. So overall, this is what we have. And I've left some space in the parentheses here because we are going to turn this into a sum of digamma functions. So the first thing we need to do is shift the index so that we are starting at n equals 0. That's shifting over 2, so we can just go ahead and add 2 in here. So we're going to have n plus 2 minus phi. Here we're going to have n plus 2 plus 1 over phi. And I'll just go ahead and substitute in, 3 plus phi. 1 plus phi. 1 plus phi because 1 over phi is just phi minus 1. Next, on the inside, I'll add 1 over n plus 1 and subtract 1 over n plus 1. And then out here, I'll subtract gamma and add gamma. If we go ahead and combine negative gamma with negative 1 over n plus 1 plus phi with this, we'll end up with 1 over 2 phi minus 1 times digamma of 1 plus phi. And if we take this positive gamma, this positive 1 over n plus 2 minus phi, and this negative 1 over n plus 1, we will end up with negative digamma of 2 minus phi. Now we want to use the reflection identity for the digamma function. So for that we need digamma of 1 minus z minus digamma of z, right? Because this is equal to pi cot of pi z. So we want this to be our 1 minus z, and we want this to be our z, right? Want this to be our z. But it's not our z yet. So as you can see, 1 minus 2 minus phi is equal to negative 1 minus phi, right? So we actually have to reorganize this a little bit in order to use our identity. Or sorry, negative 1 plus phi. So we're going to use digamma of z plus 1 equals 1 over z plus digamma of z. So this means that, if I go on the side here, digamma of 1 plus phi, oh dear, my size and my phis are getting mixed up here, is equal to 1 over phi plus digamma of phi, which is equal to 1 over phi plus 1 over phi minus 1 plus digamma of phi minus 1. So let's go ahead and make some more space. So after I just went ahead and expanded those two, the only thing that's left to do is we can go ahead and combine this fraction right here. We're going to end up with phi minus 1 and with 2 phi minus 1 over phi squared minus phi. And phi squared minus phi is just 1, right? And when we cancel this on the outside, we're going to end up just getting 1, right? 1 plus 1 over 2 phi minus 1. And then this is pi cotangent of pi times whatever this is, because as we said, digamma of 1 minus z minus digamma of z is just pi cot pi z. And since this is 1 minus 2 minus phi, then this is going to be cot of minus phi, right? And I can go ahead and simplify this real quick. So this is just going to be 2 pi minus phi. Or sorry, minus pi phi, right? And cot of 2 pi minus x is just negative cot of x. Our answer is just going to end up being 1 minus 1 over 2 phi minus 1 times pi cot of pi phi. Wow, a very golden answer indeed. I hope you guys enjoyed the video, and hopefully I'll see you next time.